Who will be speaking?
I am. If you don't mind, I can start.
Alexander Ivasyuk, please.
Yes, thank you. Good afternoon, everyone. I am Alexander Ivasyuk, and I would like to present a research by a group of authors, which is called Modeling of an Instrumentation Control System with online verification for small modular reactors. We represent 3 cities of Ukraine, as you can see now on the screen, the Kharkiv, Poltava, and Kropivnitsky. The presentation consists of 4 parts. Introduction. The second part is development block diagram INC system for SMR with online verification. The third part is development and research multi-fragment models of INC system for SMR, and conclusion. So, small modular reactors are the nuclear reactor generation 4, designed to address several challenges, such as providing electricity to remote areas, increasing the level of green energy, and reducing CO2 emission. Also, it can simplify and speeding up the construction time of nuclear power plants. SMRs aim to enhance operational safety for the environment by extensively using passive reactor protection approaches. Therefore, the number of safety functions which shall be performed by the digital INC could be reduced. One way to reduce the cost of electricity is to minimize the number of transition and the outage duration of the reactor. This can be achieved through several means. Reducing the duration and cost of scheduled preventive maintenance, reducing the likelihood of unplanned reactor shutdown due to INC failures or malfunctions, increasing the reactor's operating period between scheduled outages for maintenance. One practical approach to solving this task is using online verification to guarantee that the functions executed by the digital INC are correct. However, online verification as standalone procedure will only enable timely detection of various failures. At the same time, development of model for the operation of digital INC with online verification, based on which the system availability functions can be calculated, is a relevant scientific and practical issue. Online verification of the correctness of algorithm functioning provides the ability to detect potential failures in advance and allows for timely corrective action implement without placing the entire digital INC system into a safety state, which would otherwise automatically lead to shut down the reactor. And on the figure 1 is represented is generalized functional structure of a digital INC. The core of the digital INC is a part which is based on the safety programmable logical controller. And this part of the more detailed description of this part of the INC is shown on the figure number 2. Such part consists of 4 channels where input signals are processed, necessary calculations are performed, and when the calculated parameter values exceeds the value of set point, a corresponding signal is generated and sent to the system level, where 2 out of 4 majority logic is implemented. Each of the 4 channels is based on PLC, where different algorithms of various reactor subsystems are executed simultaneously. The goals and conditions for conducting online testing may include completing system checks in conditions that cannot be replicated during production due to complexity and cost. For example, space industry, nuclear industry. Testing non-critical functions where the cost of testing during production is higher than testing them during operation. Continuous verification of the object correct operation during its functionality to timely detect hidden failures and assess the correctness of the parameters specified in the technical requirements. During online testing, the following source of input test value are identified, which are fed into the object. External to the object under the test, such as the environment of technological process, where human impact on their formation is absent. External to the test object, but generated directly by the person conducting the test. Internal test signal generated by the test object itself. Online testing can be categorized by time interval as continuous and periodic. The set and order of input test signal divided into constant, never change, and variable, where the order in which they fit into the test object and their values can be changed over the time. This work considers a case where online testing is conducted externally, periodically, with the source being a human, while the test object also performing continuous internal self-diagnostics. The model shown on this slide is suitable for describing the operation of the digital INC. INC software may be updated due to a rising of the software fault. If the online verification is successful, the system is continuing performing the operating. However, this model does not take into account the fact that after software updating, the rising fault may remain or new fault may occur. Therefore, the previous model has been enhanced. The updated version is shown on this slide. The new multi-fragment model simulates the case when verification procedure finds out that updating software still has the fault. If it happened, the system cannot return to the state S1 as it was on previous slide. The assumptions of multi-fragment models are expanded and presented on slide 10. In right part of this slide show extended input parameters of multi-fragment models. Now you can see the market graph consists of 4 fragments of the multi-fragment model. For compactness, each fragment of the model is represented with a vertical arrangement of states. While constructing this graph of the model, the color making of the state red, green, yellow, and purple were used to distinguish the different states. Green color was used to highlight the normal operating state without any faults. Red and purple indicate that system has some type of uncovered faults, and yellow marker is used to highlight software online verification state. The channel is in this state is inoperative. The simulation results for constant values input parameters are shown on this slide now. The objective of research is the analysis of availability functions value as it's shown on this slide, depending on the different online verification procedures. The graphs illustrates the classic case when the model with online verification initially has a lower availability than the model of the system with unremediated software fault. And then over time, after the fault is fixed, the system availability is increased. Figure A shows that the presence of additional inoperable state in the second model is leveled under the condition of absolute success of the verification. At the same time, the probability that system will get into this state from the first attempt is extremely low. Figure B illustrates that the presence of an additional inoperable condition reduces the availability indicator at the initial state in the second model. The graph presented on the slide demonstrates in detail the impact of D-verification parameter on the behavior of the availability functions of the models in three-dimensional projections. Based on an analysis of the graphs, can be concluded that for the MDEP1 model, the D-verification parameter does not have any impact on the minimum value of the availability functions. Otherwise, for the MDEP2 model, there is such an effect. For all models, increasing D-verification to value 1 equal 1 increases the rate of transition of the availability functions to the steady state. And conclusion and the future step presents on the slide. The continuous of the research provides input data that could be accounted while planning the operating order of future SMRs. Based on this research, possible to reduce the outage time by optimizing the maintenance procedure of SMR and increase its operating efficiency. The choice of strategic and technology of online verification must consider all limitations in context of requirements to safety INC and either a digital infrastructure of SMR. The direction of further research is to investigate the case when the application algorithms updating based on the operation experience to increase the efficiency. Thank you for your attention. Could you turn on the microphone? Thank you.
Thank you. Thank you for your presentation. Do you have any questions?
Yes, I have one. May I ask you?
Please.
So you tell about the small modular reactor, but what is the specific for online verification for this type of nuclear reactors? Can your approach be applied to other types of nuclear reactor?
You mean could be this approach can be used in the large nuclear reactor?
Yeah.
Uh, of course, different procedure which can be performed during the operating of the uh, reactor unit is depending of many regulatory documents. And special for SMR, where the cost of generated electricity is not competitive with a large nuclear reactor, the any way which can increase this efficiency, I would say, have more probability, have more chance to be implemented. Especially, but for the large reactor, if we are talking about, for example, safety system, which is consist of 3 channels and implemented majority logic 2 out of 3, this type of online verification can be implemented with some limitation, because when we placed one of the channel into the maintenance mode by using this mode is often called bypass mode, the I would say all majority logic will be reduced, for example, in two out of 1 out of 2, if we are talking about 3-channel based INC system. But for the for example, such type architecture of the INC is proposed by the one of the I would say company which which is going to build the Kairos project. Kairos, its name company is Kairos, and the architecture of the INC safety TSC, which was submitted to the US NRC, have such type of architecture. So for SMR is more suitable because for them it's can directly lead to the increasing of efficiency. For large existing nuclear existing power plant, I will be honest, it's the probability is lower, because nuclear industry is high regulatory industry, and any change implementing very slow.
Thank you for your answer.
Thank you for your question.
One more questions, please. I have one. What can you say about the safety of your methods, of your approach, and your digital system?
Safety, when we are talking about the safety system, it means that this system have to perform the functions which from the nuclear power plant point of view is the safety. It means, for example, shut down the reactor or the functions. For example, if we are talking, about the Kairos Power proposal to build such type of safety NC system, they intend to implement the next functions. It's the in-core measurement, in-core system, X-core system, subsystem, S-fast system, and RTS, reactor trip system. So these functions is going to be implemented and performing simultaneously on the one set of hardware equipment.
Thank you.
Thank you for the question.
Any questions? No one. Thank you very much for your interesting presentation.
Thank you.